We have been talking about strength for the uniaxial tensor test, where we focused on 1D deformation, and the strength value basically is a scalar. Now let's extend the concept to 3D space and have a look of how strength describes deformation for 3D bodies. Before strength, let's quickly review how deformation or deflection is represented in 1D, 2D, and 3D spaces. It basically records the coordinates change between undeformed and deformed body. In 1D space, as shown here, the bar can only deform in the x direction and deformation can be represented by a scalar ux. For 2D space, deformation can occur in both x and y direction, so a 2x1 vector can record the deformation. Here the letter u is bold to indicate a vector. For 3D space, accordingly, we need 3 components for x, y, and z direction respectively. Hence, deformation is a 3x1 vector. Now, let's have a look of strength. For a 1D problem, as we shown by the uniaxial tensor test, strength is a scalar value, epsilon x. However, for 2D and 3D problems, strength are in a form of 2x2 matrix and 3x3 matrix. We call such matrix tensor. After showing you how the strength tensor look like, let's discuss in detail what all these components inside the strength tensor mean for describing deformation. Since 3D space is more general, we will skip the 2D case and directly discuss the 3D strength tensor. First of all, let's focus on the components along the diagonal in this 3x3 matrix. They're basically representing the uniaxial deformation in x, y, and z direction for the body. So the term epsilon xx can be called as the normal strength in x direction, and it records the uniaxial deformation in x direction. Similarly, epsilon yy is normal strength in y direction, and epsilon zz is normal strength in z direction. That's it for the diagonal terms in this strength tensor. Next, for all the off-diagonal terms, the definition will be a little more complicated, but still has clear physical meaning. Let's have a look. For the off-diagonal terms here, a very important feature of them is they're symmetric around the diagonal. That means there will be 3 pairs of off-diagonal components. So what's the definition of these off-diagonal terms and why they're symmetric? Let's look at the xy surface view of the cubic. Besides the normal deformation pattern in x and y direction, there's another deformation pattern, which is the shear deformation. And the off-diagonal components in strength tensor are used to capture such deformation. Let's have a closer observation of this shear deformation. We have an increment in x direction delta ux with respect to y dimension of the cube. On the other side, we have an increment in y direction delta uy with respect to x dimension of the cube. Delta uy over x and delta ux over y are basically the tangent values of these 2 angles. And shear strength is defined by adding up these 2 tangent values and then dividing the value by 2. Note that for small deformation, we can equal the tangent of an angle to the angle itself. So basically, the shear strength records the angle change between the 2 edges of the cube. Another look of this formulation, we can see that the terms with x and y are interchangeable, which means if we exchange location of x and y here, we'll have exactly the same expression. And this is one way to explain the symmetric feature of the shear strength components. For shear strength on x, y, and yz plane, the deformation will follow the same way. Let's have a vivid view of what kind of deformation these shear strength components are representing. So for pure shear deformation on xy surface, you can see that only faces on xy plane are having a changing angle. For all the other faces, the perpendicular corners are remained. Same thing for shear deformation on yz surface and xz surface. So after the discussion of the 9 components, we should have a clear view of the physical meaning of the strength tensor. We know that in 3D space, strength characterizes a deformation by normal and shear parts. Another look of the strength tensor. The format of this 3x3 matrix can be a pain in derivation of material relationship. So people come up with an easier notation of strength by transforming the 3x3 matrix to a vector. First, we put the 3 diagonal components in the vector. Then, since the off-diagonal terms are symmetric, we only need one of each pair to represent the shear deformation. So we put the 3 distinct off-diagonal terms in the vector. This leads to a 6x1 vector. A final step, we're putting a multiplier 2 for the shear strength terms. This is for the consistency in stress-strain relationship. In some places, shear strength with multiplier 2 is directly called engineering shear strength. So just keep in mind that in many formulations, the strength you see will be in this vector format instead of the 3x3 tensor.